moving forward in my experience, before I move ahead on the presentation, we'll be discussing a bit about what do we mean by smart grid and what is the basic agenda. Meanwhile, in my career, many things I have seen, many policies have been made, and no, not only the policies, a lot of plans have been made. States have prepared their own state energy efficiency action plan, state power action plan, state energy action plan, and few things were quite clear and straightforward. Many policies came for electrification. Similarly, many policies came to enhance the energy efficiencies. For smart grid, national smart grid mission came up into the picture, and a lot of things came up. But one thing that is quite specific today also we'll be discussing on the same, that there are few back-end calculations which every utilities or the discom do. And then second thing is there are always datas which are either present at the central level, at the ministry level, or at the state level. Okay, and you may always find some discrepancies or some deviations in those data. Just for an example, let's say you talk about Punjab. Okay, so the total renewable energy generation or capacity, or let's say total power consumption of the state of Punjab, you may find in different sources. One may be the statistical abstract of Punjab. It may tell you something about the total energy consumption of Punjab. Similarly, Niti Aayog may tell you some data, some million units of energy consumption for the state of Punjab, let's say 15,000. Similarly, there are another central electricity authority. It may also tell you about the total energy consumption of the state of Punjab. And there may be some other resources as well, some reports published as well, let's say Unnati and a few more reports by maybe Bureau of Energy Efficiency, which may tell you a bit different energy consumption for the same state. However, the energy consumption may vary, but eventually the intent is the process or the action items or the measures which the state has to take are more over the same. Okay, so many a time it does happen when at the same things people may challenge the government or may challenge the state that no, this is not true. For an example, recently in the last year you might have heard that India have provided electricity to its last village. Now India is 100% electrified, right? So many people have claimed and many people have challenged the same statement as well, that no, that's it's not true. Okay, but the moreover intent is that yes, India has been able to reach, has been able to provide electricity to the last point of the of the country. And not only that, we would be also discussing about what are the major aspects on which we would be talking, or what are the major aspects why smart grid is required. And I would be touching some basic concepts of the grid system, that how the grid system work. We would be talking about that. Then we would also be talking about what do we basically mean by power, and what is the power generation capacity, and how the state varies the power, and how after generating the power at the thermal power plant, how we are able to provide the power at the end consumer level. And these kind of steps, these kind of things we would be talking as well. Okay, so starting with us, why do we basically need a smart grid kind of system? Um, no wonder in India, majority of power generation that we are making, and this power I'm talking about is only electricity that's we are talking about today. It is the coal-based power plants through which we are generating our power, and the efficiency of those systems is anyway within a range of 28 to 35%. Now, the issue is that power plant themselves produce 50 hertz of AC electricity, and the generation voltage is somewhere in a range of 11 kV to 33 kV, kilovolt basically. Now, in your earlier classes, you might have heard that power is basically the multiple of voltage and current. Okay, so in simple terms, higher the voltage, the less would be the current in the same line. Okay, or in the similar terms, the higher the voltage, the less would be the line losses. Okay, that's what in simple terms it is being said. So now, in order to, no wonder if you are generating at 11 kilovolt and 33 kilovolt, you have to transmit this power. Okay, because you're generating it at the thermal power plant. Now, for an example, thermal power plant is somewhere in Rajasthan, Rawatbhata, and now you are generating that power and taking it to somewhere in Delhi, let's say. Okay, so now that power being transferred to somewhere in a range of 700 kilometers or 800 kilometers. So that would provide a lot of losses in the system. Now, in order to reduce those losses, we have to increase the voltage of the said line, the said power. Now, in order to increase the voltage, we require some transformers, right? So transformer, basic major two types: step up, step down. Step up basically increase the voltage, and step down basically reduce the voltage. So now then from 11 kV to or 33 kilovolt, we increase our voltage to 220 kilovolt to 400 kilovolt. Okay, so the power is basically or the voltage is basically increased to 220 kilovolt to 400 kilovolt in just in order to reduce the losses. Then in simple terms, the power losses is proportional to I square R. I is basically current and R here is resistance. Now, why we are increasing the voltage? So that the current can be reduced in the same system. Okay. So now as the current is being reduced, so the power loss would be reduced. Now, in simple term, if we see an example, if we are increasing our system from 11 kilovolt to 33 kilovolt, or if the power is raised from kV to 33 kV, so the voltage would be to 3, 1 to 3, basically the power is being increased, the voltage is being increased, and then the line losses would be lowered by a factor of, this is I square R. So basically 1 upon 3, the square of 1 upon 3, which is basically 1 upon 9. So the line losses will be lowered by a factor of 1 by 9, and the voltage drop will be lowered by a factor of 1 by 3 if we are increasing to 11 or 1 ratio 3, or if we are increasing the voltage from 11 kilovolt to 33 kilovolt. So the basic agenda is to, the line loss would be square of the current. That's what the basic terms mean. Now, there is another kind of losses which is termed as technical losses. We would be talking about all of these things. Two majority losses are there: technical losses and commercial loss, which we would be talking on today. Standard technical losses are around 17% in India, and then some states shows their transmission and distribution losses in a range of 17 to 50%. And could you please hold on a second? All right. So basically, the standard technical losses in India is around 17%. Now, similar example is of Kashmir. In Kashmir, the standard technical losses is somewhere around 50%. Okay, that's what the Discom specifically mentions, that we, the losses they have is somewhere in a range of 50%. And sometimes the losses are always not only technical, that okay, we have distribution losses, the transformers are undersized, the feeder panels are undersized. It's not always the technical losses are there are sometimes the unmetered and pilferage losses as well. Now, unmetered means when the system is not metered. For an example, many of you might have heard that in Punjab the electricity for farmers is free. Okay, but no wonder for a small system, let's say 1 HP motor or 3 HP motor or 5 HP motor, every farmer do not have their own meters, right? So these kind of systems are basically termed as unmetered system. So unmetered system in which the Discom authority itself assume that this much would be somewhat the energy consumption of the motor, so they just take the reading accordingly. Okay, and then there is pilferage losses, which basically means that stealing of electricity. Okay, then there are some basic terminologies. Now we would understand that how we are mentioning this number, standard technical losses, around 17% in India. Okay, so now we'll talk about that how we have reached to this number, the standard technical losses. In order to get that standard technical loss, there is a terminology named as cascade efficiency. Now, what does this mean? Cascade efficiency means that from the generation point, let's say from the thermal power plant, or whatsoever plant is there, either thermal, wind, nuclear, or whatsoever, after that generation point, to make the electricity reach to the end user, whatsoever system you have used, the multiplication or the product of the efficiency of each system. Okay, that's what is meant as cascade efficiency. Just for an example, at first you have generated your own electricity at the thermal power plant. Okay, and you have generated in a range of 11 to 33 kilovolt. Then at the step up station, this is the first point where you have increased your voltage to extra high voltage transmission, and where you have losses of somewhat around 0.5%. So the efficiency of the system is 99.5%. Then again, there would be some substations. There are another losses is somewhere in a range of 1%. Efficiency is 99%. Then you, when you come to the nearby system, at some places you require a reduced voltage. So you have further reduced your high system to high voltage transmission, and this is in a range of 220 to 400 kilovolt, and the losses is maximum losses around 2.5%, or efficiency is 97.5%. Then sub transmission, 66 to 132 kilovolt, and the maximum losses is 4%, efficiency 96%. Then you have further stepped it down. This is, you might have seen in nearby your households, the lines you see, 11 kilovolt to 33 kilovolt. Step after stepping it down, the losses, another losses are 0.5%, and efficiency is 99.5%. And then finally to the primary distribution, finally to the end user, basically 11 to 33 kilovolt, and 5% are the maximum losses, and efficiency is 95%. So now, what do we mean by the cascade efficiency? Efficiency 2 multiplied by efficiency 3 multiplied by efficiency 4, 5, 6, and 7. The multiplication of all these would provide you a final number. So here, if you see, the cascade efficiency of transmission and distribution system from the output of the power plant is, so first system has an efficiency of 99.5, so 0.995 multiplied by, then 0.99 is the second system efficiency, then 0.975 third system efficiency, then 0.96, and then 0.995, and then final system efficiency is 0.95. So overall we reach to a number of somewhat around 87%. So here it shows that okay, 13% are basically the losses we have reached. But in India, the standard technical losses are somewhere around 17%. And but this is at the left. This is how I told you that how utilities calculate their own losses in the system, basically. Um, but there is also a true terminology that many states directly claim that they have their own technical losses in a range of 17 to 50%. Okay? That not only every time there are technical losses, there are sometimes commercial losses as well. Sometimes there are some other sort of losses as well, which we would be talking today. Okay, then we're discussing about that how smart grid can help in reducing these kind of losses. So now let us say this is the total system efficiency. Let's say you have reached to a number of somewhat around 87%. Okay, so it is basically, if you've generated one unit, you are using somewhat around 0.87 into at the end user. Okay, there is further 37% reduction if you are having a belt driven system. Okay, at the end user. For an example, if I'm using a motor and a belt driven system, I have, let's say, an air handling unit or whatsoever. If I have a belt driven system, there is further 37% of losses, and that's why my total efficiency of the system then reduces to 50% only. All right, it's not because of the government losses, or basically the technical or technical losses are somewhat just in a range of 17%. The rest of the losses are due to, if I'm using a motor system, if I'm using a belt driven system. So these are the mechanical losses which are basically in our system. So because of that, it is being generally said that 1 unit saved is equals to 2 units generated. So it means if you are generating 2 units, after all the losses, you will get 1 unit of electricity. I mean, or you could say the output you would get is basically 1 unit. So 2 units generated is 1 unit saved. That's why Bureau of Energy Efficiency is very focused onto this specific statement, and this is how they are getting it. Now, before we move on the smart grid, first we need to understand how the billing is done. Okay, and whenever we have our own electricity bill, what do we see? And by today, after this class, or by the way, is everybody okay with the language? Though I'm speaking in English, but if anybody wants me to switch the language, I'm pretty much okay with that as well. So please let me know if you're okay with the language or if you have any
That's good,
issue.
sir.
You good? Oh, cool, cool. All right. So before we talk about the smart grid part and everything, few things that we really need to understand is that how the electricity bill is being prepared, or what aspects of the electricity bill we have to look into. Hold on a second. Do I have received a message? Let me see. Mm, okay, I don't know. Anyway, the screen is visible, right? Hmm. So now we whenever you today also, if whenever you go home, make sure you see your electricity bill. Okay, you every time we just talk about few things, that okay, electricity bill, this is the total unit we have generated, total unit we have consumed, and this is the total electricity consumption. Okay, but today you would be seeing few more things into your electricity bill. Before we move to that part as well, I would like to ask you guys, what do you mean by 1 unit of electricity? You say 1 unit of energy consumption, right? We always talk about that. Okay, how many units we have consumed? Let's say 50 units, 100 units. What do we mean by 1 unit? You may write in the chat box as well. Or if here we go. Yes. What do we mean by 1 unit of energy or 1 unit of electricity? Everybody might have listened to that part, right? We always say that okay, this much unit of energy is being consumed, these many units are being consumed, electrical or mechanical or whatsoever. You might have seen your own electricity bills, so you always see that okay, energy consumption is there, these many units consumed. What do we mean
This
by
is
1 unit?
1 kilowatt hour, like that.
Yes, 1 kilowatt hour. That's cool. All right. So basically, in simple terms, if I say that I have, yeah, right, everybody is written well, 1 kilowatt hour or 100 watt, 1000 watt hour. Um, in simple terms, let's say if I have a 100 watt bulb and if I'm running it for 10 hour, it is basically 100 watt multiplied by 10 hour. It makes it 1000 watt hour, right? Or basically 1 kilowatt hour, and 1 kilowatt hour is basically means 1 unit. So just in the same similar manner, there are several many systems into our building. Let's say you have an AC which consumes somewhat around 1 kilowatt. Uh, when you run it for 1 hour, it makes 1 unit of electricity consumed. So an AC being running for 1 hour, somebody consumes around 1 unit. Similarly, lights, similarly fans, whenever they runs for the whole month, they calculate the total units being consumed through the meter. Now, apart from the kilowatt hour, there are few more things which the electricity bill includes, and it may be a possibility that for our smaller household units, you won't find all of these things. Okay, but for the bigger industries or for the industrial units or for the bigger buildings, you will always find these kind of things into your electricity bill. One, the maximum demand charges. We would also discuss about how to calculate the maximum demand. We'll talk about that as well. Then energy charges, which basically includes kilowatt hour charges or kVARS charges or kilovolt ampere hour charges. These three things you may also find into the electricity bills. Initial electricity bills only talk about kilowatt hour. They only used to take the charges from kilowatt hour. Now the utilities are also taking charges for kilovolt kVAH as well. Then third one is power factor penalty. If you have a lower power factor, in that case power factor penalties is also something that the utility grid takes from you. Then there may be a few more things like meter rental, electricity duty charges, and then if peak rates, if are there any, I mean, usually utilities do not have this part, but if the industries have any peak rates, so they would be charged for a peak rate as well. Penalty for exceeding the contract demand, that is also another thing. And then finally is the surcharge of metering, that is also the utilities charge in the same electricity bill. Now the problem is the meter we have is an electromagnetic meter. Okay, so what we get from the meter is the kilowatt hour, that how much active energy is being consumed. Now this is basically, for an example, if you are running a motor. Okay, so at first you are provided it the electricity, but there is some electricity which is being consumed to sustain the magnetic field in the motor. Okay, so that power is not of much use for you. Okay, until unless when the magnetic field is being sustained, then the motor will start running. Okay, so the power that you are getting is basically the active energies only, which is used to run the motor. But there is reactive, there is some more energy which is, or in simple terms, there is the power that is being required to sustain the electric field or sustain the magnetic field is basically your reactive energy. And then there is you, the total of both is the final energy or the apparent energy, basically you which you get. Now based on the same part, how they calculate the maximum demand. Okay, so every utility, they calculate the maximum demand over a recording cycle of 30 minutes, right? So how do they do that? So for an example, if you are having an industry in which you are having the same meter, and through the meter one get to know that okay, in a cycle of 30 minutes they are recording it. For an example, for the first for 4 minutes the maximum demand reached to somewhere around 2500 kilowatt ampere. Then for 12 minutes the maximum demand is 3600 kilowatt ampere. Now always remember, if after if, I mean in these 30 minutes they will only take the maximum four numbers. Okay, they won't take the number that is below this. For an example, if the lowest number is 2500, they won't take any other number lower than 2500. Any number above 2500 will count under the maximum demand. Okay, then 3600 for 12 minutes, and then 4100 kilovolt ampere for 6 minutes, and then 3800 kilovolt ampere for 8 minutes. So the maximum demand recorder, how it will calculate the maximum demand: 2500 into 4, then 3600 into 12 minutes, plus 4100 into 6 minutes, and then 3800 into 8 minutes, and then divided by the total of all these minutes. 12 plus 4 16, plus 6 22, and plus 8 30, divided by 30. And this is how you will get your maximum demand: 36.06 3606.7 kilovolt ampere. Now you might feel that okay, 3606.7 kilovolt ampere, and this is the maximum demand that you are getting, and you will be charged for this. No, you will not be charged for this. You would be charged for the maximum demand that you are getting, which is 4100 kilovolt ampere. This is your average demand. Okay, so even if the average maximum demand is low, industry has to pay for the maximum demand charges for the highest value registered. So industry, in this case, industry has to pay for 4100. Okay, if this number is lower than the maximum demand, then that's fine. But anyway, if this value goes above the maximum demand, one has to pay for the total part. Okay, or one has to pay the maximum demand charges, and that is on the basis of for what value it is the highest one. Okay, but until unless if this is within a range, then it's fine. But if it is not, one has to pay for the maximum demand charges. All right, now this is these few things are done. Maximum demand is done. We get to know that what our electricity bill shows, and then we have also talked about the cascade efficiency, or the how they calculate the efficiency. Now the third link is the transformer. Okay, what do a transformer do, and how they are increasing the efficiency of the transformer. Then we will compile all of these links into the system, that okay, this is cascade efficiency, this is the billing efficiency, these are the technical losses, and how smart grid is finding solutions to all of these systems or all of these losses. Then now transformer, the basic terminology we everybody knows. It has two or more coils, and one is onto the left, another one is onto the right, and which are electrically insulated and magnetically linked. And primary coil, which is we connect it to the power source, and secondary we connect to the load. Turn ratio is turns of the secondary divided by the turns of the primary. And two major types of transformer: One is power transformer, which are used to transmit higher voltages, and then distribution transformer, which you find nearby your homes for low voltage distribution network. The problem with transformers is there are two major types of losses in the transformer. One is load losses, and another one is no load losses. Load losses basically directly means that when the transformer is running, okay, and when you run the transformer, there are losses in these windings, which the windings are there basically. So in these windings there are always losses due to the resistance of these windings. So due to that losses, it is termed as load losses. Okay, the load loss basically means due to the resistance of these windings, the loss you get are the load losses. There are another type of loss, which is the no load losses, which is basically the power which the transformer consumes to sustain the magnetic field. Okay, every transformer would definitely have the no load losses. They may further reduce the load loss, but no load losses are always there, and which is basically the power the transformer require to sustain the magnetic field. Okay, or in another terms, you may get the same terminology by another name. You may find it by the name of the core losses, or whenever you energize the transformer, and you would if you are energizing the transformer, you the core losses would always be there. And the different part is because this power the transformer always require to sustain the magnetic field, this losses do not vary with the load. It doesn't matter if you're increasing the load on the transformer or reducing the load on the transformer, this losses would remain constant. Okay, because these are the no load losses. All right, so these are the majorly two types of losses. Now, what are the new age transformer doing? How the new age transformers are providing energy efficiency to the system? Initially, the transformer was made up of silicon alloyed iron. Nowadays, they are using amorphous material or a metallic glass kind of alloy for the core of the transformer. And now, as they are using amorphous material, they are able to reduce their overall losses to a huge number. Okay, and nowadays the transformers are able to achieve an efficiency of somewhere around 98.5%, 99% of efficiency of the transformers, which are easily being achieved nowadays. Apart from that, whenever buildings they choose transformer, they follow few codes also. That is another aspect, that how they are providing energy efficiency. They mandate that the transformer you will go for shall not have the losses more than this particular number. Okay, so for an example, if you're using it 2000 kilowatt ampere transformer, they will initially tell you that okay, the losses should not be more than 5850 watts. So in that case, you first check the transformer that okay, the losses are less than this, so the transformer is efficient than the minimum, efficient than the maximum value being provided. So this is how at every level the government is trying to provide efficiency to the system. Now we have two major kind of losses, which we are talking about: the technical losses and the commercial losses. We have talked about the transformer and distribution losses, and then basically high I square R losses, or simpler terms, transmission losses in distribution line due to inherent resistance and poor power factor in the electrical network. These are the transformation losses. Now, what are the reasons for technical losses? One is the lengthy distribution lines, inadequate size of the conductors, voltage regulation, distribution transformer not located at the load center. This is very important aspect. I have been in touch with several utility companies. They usually find it, and in fact you also might find nearby your home, you always see a transformer nearby, right? So the target or the try of the government is always to keep the transformer located at the load center, okay, so that the end consumers do not get a reduced voltage. So for an example, the transformer at the outer end providing you 410 volt, okay, but at the end, or the end consumer is not getting enough voltage. Reason being because of the losses or whatsoever. So that's why the always try is to provide the transformer nearest to the consumer, or to keep the transformer located at the load center. And then the last one is the low power factor. And then there is below example which shows that okay, if there are two loads, both are 300 kilovolt, both are 300 kilowatt, and then first have a power factor of 0.7, and then the second has a power factor of 1. And then you see that how the current is being reduced. At first you are using 38.9 ampere, in the second case you have 27.2. Similarly, line losses is further being reduced to 27.2 kilowatt, and then for the second system which has a higher power factor, line losses is being further reduced to 13.4 only. So that's why if the power factor is low, the system would have a higher losses into it, and that's why it is being specifically, the utilities also provide penalties if you are having a lower power factor. So the power factor near to one is better. There are few codes as well, such as Energy Conservation Building Code. It mandates to have power factor in a range of 0.97 to 1. Initially, it was 0.95 to 1. Now it is being increased in 2017 to 0.97 to 1. All right. Then there is another type of losses, which is the commercial loss, which basically includes three things. One is the meter reading, that if there is a discrepancy in the reading of the meter, or second thing, if the meter is being out of order, or the third thing is if the meter is unable, or if the utility is unable to trace the meter, or the meter is being disconnected or whatsoever. These are the meter reading losses, which are basically the commercial loss. Then the second thing is metering. And then, I mean, if somebody has tempered the meter, and in various forms, metering is the second thing. And then the third thing is the collection efficiency. Collection efficiency means that, okay, these many units have been built. For an example, the utility themselves has generated these many units, and then these many units have been metered. I mean, they are able to trace that, okay, out of 10 million units, 9 million units, they have traced that, okay, for these 9 million units, they have generated the bill. Now, out of these 9 million units, the amount they have achieved, or the amount they have received, is only for 8 million units. So that's what the collection efficiency is. They are not able to collect the whole amount from the people, and that's where the collection efficiency stands. So these are the commercial losses below ones, and the above one are the technical losses. That, okay, what are the technical loss into the grid system, which basically are due to the four reasons. Just remember these four reasons. One is distribution transformer not located at the center, low power factor, and the conductor size is not appropriate, or maybe the feeder size is not appropriate, distribution lines are lengthy, and then voltage regulation, or the voltage drops basically, are the major cause of the technical losses. Now, how do they calculate these losses? So first we'll talk about the technical losses. How do they calculate that? Commercial losses are very easy to calculate. Okay, there are two things: billing efficiency and collection efficiency. Billing efficiency means that how many units you have sold divided by how many units you have generated. Collection efficiency, how much revenue you have collected divided by the total amount billed. So straightforward. Commercial losses are very straightforward. That how much unit you have generated, and how much unit you have provided to people, or how much units you have sold. But in order to determine the technical losses, here the utilities get into some issues. So they use basically two methods. One is the direct method, and another one is the indirect method. Now, direct method basically means that you provide meters, or the electricity meter, from starting from the input point to the individual consumers. Okay. So in direct method, you are providing electricity meters, or the energy meter, the normal meters that we have at our home, at all the locations. Okay, starting from the input point to the individual consumers. Everywhere you have meters. So from that meter, you see that, okay, these many units you have generated, and then from those meter readings, you get to know that, okay, these many units have been consumed by the people. Rest goes to your technical losses, or the transmission and distribution losses. Then there is another method, which is indirect method. In indirect method, instead of getting the power, or instead of getting the numbers, or instead of getting the energy consumption from each consumer, we take that number at the substation and feeders. We provide energy meter at critical locations such as substations and feeders, and then we also take network information, that, okay, these are our electricity meters which we are providing at substation and feeders, and then we have our own network, such as line, the length of our total transmission line, the feeders, the size of the conductors, the capacitors, etc., etc. Okay. Now then, based on that, we calculate that, okay, these many watts per kilometer it should be the losses, but now we are reaching to a higher number. So based on that, we determine that, okay, through that indirect method, in which we also calculate the length of the line, conductor size, type of conductor, and everything into our system. And then finally, we also conduct load flow studies that, okay, during the peak load, we get a higher consumption and kind of that stuff. And then we use, there are also some suitable softwares as well, which the electrical engineers basically use to determine the total technical losses in their system. Then there are some basic formulas for AT and C losses, transmission and distribution losses, to determine that transmission and distribution losses. And apart from that, the basic terminology to include both the technical and commercial losses. So the aggregate technical and commercial losses, how do they calculate it? Is AT&C losses is equals to 1 minus billing efficiency multiplied by the collection efficiency multiplied by 100. Okay. So what do they want to know is that how much is their technical and commercial losses into the system. So for an example, if they have a billing efficiency of, let's say, 0.9, and then the collection efficiency of 0.9 as well, let's say. Okay. So 1 minus 0.81, which is around 19. So they say that, okay, our losses are somewhere in the range of 19%. Now, there are two terminologies which is being used here. Transmission, this is technical and commercial losses, aggregate technical and commercial losses is 1 minus billing efficiency multiplied by the collection efficiency. So what does the billing efficiency means? Billing efficiency means that, okay, these many units we have sold divided by the total input, or the basically total energy units generated. Total units sold in million units divided by total units generated multiplied by 100. Similarly, collection efficiency, revenue collected, that how much revenue you have collected divided by the total amount billed into 100. I have also taken an example, we'll talk about that later, of calculating these AT&C losses. But if you want to write, you can write these formulas, which may be useful, that how do they calculate the technical and commercial losses. Then how they can reduce the technical losses, and similarly how they can reduce the commercial losses into their own system. One is high voltage distribution system. This is pretty straightforward. In your older times, if you remember in your childhood, you might not have seen 11 kilovolt or 33 kilovolt line going nearby your houses, right? You always see that, okay, this is 240 volt line, or the smaller lines you might have seen nearby your houses. But now, as the system has increased, or the as now the infrastructure has a higher load on it, and more people are coming to the same city, and the cities are becoming centric. So now it has become difficult to provide the power at the same voltage. Reason being, the losses are being increased, and you cannot transmit the power at a lower voltage, because just because the losses would be higher in that case. So that's why one thing which is a specific suggestion, that how we can reduce the technical losses, is a high voltage distribution system, that they have to implement distribution system at a higher voltage. And low transmission distribution, they have to reduce it, or in fact eliminate it wherever they are feasible to do it. Then the second is the amorphous core transformer. Basically, we have talked about the transformer. Nowadays, we are getting amorphous core transformer, which are having a higher efficiency of 98%, in fact. So transformer replacement is also another thing on which the government is working. Then the second part is the commercial losses, how we can reduce our commercial losses. Now, in order to reduce the commercial losses, there are a few things. One is accurate metering. So there may be a possibility of post calculating their own technical losses, that the metering should be more accurate, the meter should be calibrated properly, or with time to time, or frequent calibration of those meters should be there, range of the meter, and then installation of electronic meter with tamper proof and remote reading facility. Then intensive inspections are specifically required. Then compulsory metering should be there. Use of energy audit could be an aspect to reduce the losses. And then finally is the eradication of theft. Now, if you also see, for an example, we are living in Punjab right away, and if you are taking a new electricity consumption, you might find that the electricity department would come at your home. They would inspect the facility, that, okay, how much load you are applying for, and then they provide you a meter for the same, and then the same meter is being tapped with the electricity connection, or with the electricity grid lines, and those are getting into your colony, or which are basically connected to the nearby transformer. So you would get that meter. But there is also another aspect of commercial losses. So for an example, we might have seen a lot of time people use the electricity directly without metering. So that part comes under the commercial losses. And then the other things which are high voltage distribution system and amorphous core transformer, which may be used to reduce the technical losses. Now, this is a clear and straightforward example. If you want to write it, you can do that as well. That how one can estimate the aggregate technical and commercial losses. So, for an example, initially is you are getting an input energy that okay, this is the total energy generated, out of which this much is the imported energy and this much is the exported energy. You have to reduce, you have to subtract both, and then you get the total input energy. The total input energy you are getting is 10 million units, let's say. Okay, EI is the 10 million units. Then out of these 10 million units, you are having some metered units, which means from the meter readings, you are able to determine that, okay, 6 million units is the metered reading. Okay. Then you get energy billed, basically the unmetered units, let's say, which is 1 million units. Now, what is unmetered units? As I initially told you in an example, there are also some readings where the discom do not have the meters directly being installed. Instead of those meters, discom itself, but they consumes electricity. For an example, several farmers consumes electricity without meters as well. Okay, but as they are using the pumps, so the government estimate that, or the government in the sense the discom estimates that okay, this much energy is being consumed by that electricity pump. So they just take that number into consideration. So let's say 1 million unit is that unmetered electricity, and then 6 million unit is your metered electricity. So the total energy billed would be somewhat around 7 million units. Okay, this is your total billed power. Then in order to this is your 7 million units. Now each unit have a cost, let's say 10 rupees or whatsoever. So how much amount billed in rupees lakh is somewhat around 400, let's say. And then out of this total billed unit, you're able to collect rupees 410 lakhs. Okay, how let's say penalties and a few more stuffs into consideration, late billing and whatsoever, you are able to collect the gross amount of 410. Okay, and the total amount billed was 400. Then arrears collected. Arrears means, let's say somebody has provided you the bill of last month or whatsoever, or let's say 6 months bills were pending, so that you have collected somewhat around 40 lakhs. Okay, so how much amount is being collected within this month, which is 410, the total gross amount collected minus the amounts collected for last month energy consumption, 40. Okay, so 370 is your total amount collected. So what was the billing efficiency? Amount collected, how much the amount you have collected, the total collection efficiency, the how much amount you have collected, and we divide it by the total amount billed. So 370 divided by 400, which is point number 6. 370 divided by 400, which is 93%, is your collection efficiency of the system. Similarly, what is the billing efficiency of the system? The total energy billed. How much is the total energy billed? Which is around 7 million units. And then we divide it by the total energy input, which is around 10 million units. So 7 by 10, which is around 70%, is your total billing efficiency. So what is the aggregate technical and commercial losses? 1 minus billing efficiency into collection efficiency. So 1 minus 0.7 multiplied by 0.93 multiplied by 100, which is somewhat around 35%, is the total losses of this system into technical and commercial losses. So this is one example. If you want to write it, you can do that as well. This is how the utilities calculate their own electricity bills. Okay, or their own technical and commercial losses. This is how utilities do that part. I'm just telling it for your own brief understanding that okay, how utilities calculate their own technical and commercial part, and this is on this basis they say that okay, this is their technical losses or this is their commercial losses, and this is their technical losses. This is how they are, and based on that they provide more funds to their infrastructure to to reduce their technical and commercial losses. And that's how the basic system works. No, aggregate technical and commercial losses, 1 minus billing efficiency into commercial efficiency, collection efficiency. All right. Then post this that okay, 10 units is being input energy and after 35% efficiency, somewhere around 6.5 is being consumed, let's say. Okay. Now, there is another aspect which is very popular nowadays, which is the demand side management. Okay. So now, what does demand side management means? For an example, at your home, you are having or you have taken a connected load of 7 kilowatt. Okay, 7 kilowatt of the total load you have taken. Okay, in this 7 kilowatt, you say that okay, I have 4 AC at my home of, let's say, 1 kilowatt each. You say that okay, I have a one water motor as well, which is somewhat around 2 HP or 1.5 HP. Okay, then you say that okay, I have few fans and lighting and a few more things, which is somewhat around 1 kilowatt approximately, let's say. And then you say that okay, this is the major things that 4 or 5 AC, and I have taken a total load of, let's say, 6.5 kilowatt. Okay, so you have 4 ACs of 4 kilowatt, then 1.5 HP motor, which is somewhat around 1 kilowatt approximately. So 4 plus 1, 5, and then 1 kilowatt of fans and lighting and everything. 4, 5, 6. 6 kilowatt you have taken, and you say that okay, my connected load is somewhat around 6 kilowatt. Now, let's say you are using a hair dryer at your home. Okay, so how much that has increased the load? Hair dryer, let's say it is of 2 kilowatt. Okay, so 4, 5, 6, and 2 kilowatt further, so 8 kilowatt is your total load that you are taking at your home at present. Okay, and let's say everything is running at the same time. So this is now 8 kilowatt that you are using. Now take it at a broader level. Okay, let's say there are 1,000 industries, or let's say there are 20 industries at a particular point. Okay, at a particular location, and every industry is of let's say dairy industry is there. Okay, and every industry in the afternoon part, or in the noon part, when the temperature is higher, they use their ACs to cool down the food whatsoever they have in the industry. Okay, now, at the same time, you would find that every industry running their AC on, the demand on the utility will increase, right? Because every industry, let's say every industry have 500 ton AC, okay, and which basically means somewhat around 350 kilowatt for one industry. Let's say 100 industries are there, so 350 into 100, this much load is being increased in every afternoon from 2 to 4 p.m. Okay, so now this at the consumer level, how one can manage the demand in order to reduce, or in order to, or to how to manage the demand, how the consumers have to manage the demand, so that the new generating plants cannot be avoided. Okay, just for these 2 hours when the industry has to run their ACs, it does not mean that the utility or the utility will prepare or will build one more thermal power plant just to meet the demand for these 2 hours. Okay. Instead, what they would do is they will ask some other industry. Let us say if you are having dairy industry, these 100 industries are in Rajpura, let's say. Okay. And the same utility is providing electricity to Patiala as well. Okay. So what they would do is they would reduce their power which they are providing to the Patiala industry. They would say that okay, from 2 to 4 p.m. You may shed your loads. Okay, you may reduce your loads. You may do some other kind of manufacturing. You may shut down your motor loads, or whatsoever. You may reduce your AC consumption, and the same power they could transmit to the Rajpura industries. Okay, this is how the management is being done. This is what they mean by demand side management. It means managing the demand at the consumer level. Now, in order to do that how the government is trying to manage the demand at the consumer level, the agenda is to reduce their own energy consumption. First thing is that, okay, so that every building or every industry, they do not reach more than their peak demand. Okay, or if they are reaching it, the peak demand, initially the utility get to know that okay, this is the time when they will reach their peak demand, or if this is the time when they would require more energy, so that the utility will be able to manage the same. So no wonder there is a higher demand of electricity which is being increased, which the rapid increment of the same electricity is there, of energy consumption is there. Now, when utility provides you the power, let us say you have taken a demand of 8 kilowatt or 10 kilowatt, the utility is liable to provide you the same. Okay, but for an instance, let's say within a range of 10 minutes only, you are using a microwave oven as well at your home, and you're using this at the same time you are using a hair dryer as well. So when you are using both of these things together, the demand is being increased, okay, of your home. Now you are instead of 10 kilowatt, you are using 15 kilowatt. So just for this extra 5 kilowatt, which you will probably use only for 10 to 15 minutes, it does not mean that more thermal power plants to be established, okay, now, or more wind system, or let's say more solar power is being used, because the power that the solar would generate will only be used for 15 minutes, right? So instead of doing that, the part for 15 minutes could be managed, okay, the 15 minutes power could be managed by some other sources, or by some other meaning. So I'll just give an example how the industries do it. Long back, I did an energy audit for the industries. So in that, we provided few suggestions to them. One is, at the same time we prepare their load profile, that okay, in the 24 hours how the system load increases. Okay, so in the noon time they used to turn their ACs on. Similarly, the motors used to run at the same time, and a lot more things were there. So one thing we tried was to shed the loads at the peak hours. So peak hours was noon. So at that time, we try to turn their motors off, which are not directly being used. So the water motors, which they use to turn the to take the water in, or whatsoever, we ask them to have their own water tanks, big water tanks of 15,000 liters, 30,000 liters, and then they turn their motor on in the morning time, so that they reduce their peak demand in the noon time. Okay, so all the motors being run at the daytime, in the morning time, all the water tanks being filled, and then the water directly being used from the water tanks. And in the noon time, when they used to turn their ACs on, the motors are being turned off. Similarly, when they have to turn their ACs on, they reduce the temperature of the building from 44 degree Fahrenheit, 44 degree centigrade to 24 degree centigrade. Now, in order to avoid that part as well, what we suggested them that instead of cooling the building through water, uh, they turn their chillers on in the night time. So they provided thermal storage as well to their building. And what they used to do is, in the night time they use their chillers. Chillers are basically big ACs which cool the water, basically just take that part, and that water is being used to cool the building. Okay, now they turned their chiller on in the night time a day before, and in the night time from that chiller they prepared ice, and then they used the ice the next day in the noon time to cool the building. Okay, so now when there is no peak time, or when there is reduced ambient temperature, they prepared the ice, so the chiller load is being reduced, and then they use the same ice in the daytime to cool the building. Okay, so this is how they reduce their peak demand. So just in the similar manner, government or the uh, different industries are reducing their own peak demand, and that's what demand side management basically means. Apart from that, government is also taking some initiatives for demand side management. Energy reduction programs are there, Ujala schemes, LED lights are being distributed, and similarly inverter ACs are being provided at a subsidized rate, and a few more programs are running. Load management programs are there, and then they provide tariff incentives, penalties also being implemented, mandated if the building proceed ahead above the peak demand. So, what is the objective of demand side management? To improve the efficiency of the energy system, reliability and quality of power supply, reduce financial needs to build new energy facilities, minimize adverse environmental impacts, reduce power shortages, and lower the cost of delivered energy to consumers. Now, how a smart grid could help us? So one, the major part is smart grid. For an example, at now you see that okay, there is only one way communication into our home. You have a meter, you have the wire that is being connected from the grid to the meter, and then you get electricity at your home, right? That's one way communication. Now smart grid wants the connection to be two way. Okay, and it is not only electricity connection, it is data flow as well. Okay, so that the grid can get to know that okay, in these times your particular area will have the peak demand. Okay, so that the grid can initially get to know. Similarly, If the grid will get to know that, the grid will able to respond faster to any error or if there is any issue. So two-way digital communication would be a more, and this two-way digital communication would provide an efficient distribution system to the state or to the city. It has also few more benefits. The smart grid system is able to repair itself directly. So for an example, if there is a power outage, the distribution system would switch to another distribution area and then it would provide you the electricity. So it, you may say that this may provide 24/7 electricity to the state. It will also provide monitoring, control, communication, as well as analysis within the supply chain. It will also provide you the shortest and the efficient ways to proceed ahead. The system will also provide consistent power supply and power leak proof ability. This is also the benefit of smart grid system. And the main aim is anyway to reduce the energy cost and consumption, as well as to improve the reliability and transparency of the energy supply chain. So now, as most of the homes have internet connection, so smart grid mission, India's target of meeting the smart grid is moreover possible. So basically, initially we used to have electromechanical meters. Now the smart grid meters want it's to be digital meters. Instead of one-way communication, smart grid wants it to be two-way communication, so that the grid also get to know that what are your requirements, and you may have the same into your application and whatsoever. And then there is centralized generation. Instead of that, distributed generation could be there. More sensors, use of more sensors, self monitoring could be there, self healing system, adaptive and aligning, and then many customer choices you would be able to get through that part. And then from your mobile application, and then there are smart automated devices are also coming into the market, which would turn itself off when you are going above the peak demand and kind of that stuff, which are basically being there. Major advantages and disadvantages. Advantages, we get to know that okay, reduced equipment failure because the system will be automatic. Electricity cost and meter cost would be reduced because anyway, as the system becomes smart grid, so one do not have to come at the site to check that how much energy you have consumed. Everything would be online, and the system itself is very efficient and automatic system, so there would not be any electricity losses and chances of the blackout and kind of that. Now, what could be the disadvantages? One is one has to prepare continuous and stable network. So the network must be stable, right? Because if there is any lack of internet somewhere, so in that case, the communication would not be established, and or one may not get to know that okay, how much energy is being there or whatsoever. Then similarly, rainy system, or if there is heavy rain, stormy wind, flood or whatsoever, that could be a big challenge for the smart grid technology. And then finally is the privacy of the meter, which is being integrated with the internet. If the meter is connected to the internet, hacking and kind of that system could also happen. So that's why a smart metering or the smart grid could be a sort of challenges. Could be that could be a challenge to the smart grid system. For more information, you may visit to https www.nsgm.gov.in, which is the National Smart Grid Mission of India, and you would find a lot of information about the same system of National Smart Grid Mission. India has provided a huge fund on the same thing, and not only the fund, India has also taken a lot of the aspects into consideration for a few demonstration project for smart grid. So that would be very helpful if you want to learn more and more about the same thing. So moving ahead, a small video on smart grid, and then we'll be talking about rural electrification as well. Are you able to hear the audio?
No, audio is not there.
Yes, yes, we are able to.
You are able to?
No, sir, not
Okay,
audible.
hold on a second.
Maniji, maybe if it is elsewhere in the file location, then you can open that particular file and then just share only that particular tab. You can stop presenting, and then instead of
Mhm.
entire screen, do the share of this particular window only. Then
Yeah,
the audio
I'll
will
do
be
that.
there.
Yes, I'm trying to do that.
Yeah, so you can stop presenting and then again just choose that particular window.
Hold on a second. Hold on, I'll just reshare it. All right. One second. Is there any way I could share the audio as well, or the audio will be automatically being connected? Maybe you're muted, I guess. Yep. All right, hold on a second. Uh, Here we go.
Maniji, have you chosen this particular window only when you did screen share?
No, I have shared my whole screen, so the video
No,
I have
don't
turned
do
from the
whole
video.
screen. This is Google Chrome, na? So when you're doing present now, then it will have option. Just choose this particular Google Chrome screen only.
All right. Are you able to see the video or not?
We are able to see the video, but not the audio.
I know the audio. Okay, hold on a second. Let me see. Hmm. All right. I guess you probably would be able to hear it now.
Electric grid was conceived more than
Yes, we
100
can hear
years
you.
ago when electricity needs were simple. Power generation was localized and built around communities. Most homes had only small energy demands, such as a few light bulbs and a radio. The grid was designed for utilities to deliver electricity to consumers' homes and then bill them once a month. This limited one-way interaction makes it difficult for the grid to respond.
Hold on a second. I just have to reshare it. The
Yeah, the
video is not.
video is quite big right now. It's not clear.
Yeah, yeah. Hold on a second. Mm, nice.
Our current electric grid was conceived more than one.
Wait. I'll open saving. Hold on.
deliver electricity to consumers' homes and then bill them once a month. This limited one-way interaction makes it difficult for the grid to respond to the ever-changing and rising energy demands of the 21st century. The smart grid introduces a two-way dialogue where electricity and information can be exchanged between the utility and its customers. It's a developing network of communications, controls, computers, integrate and plug-in electric vehicle charging. With our participation, the smart grid or communicate with us to our the
Manoj, we
smart
cannot
home
see
communicates
anything
with the
right
grid
now.
and enables
Meanwhile,
consumers
if
to
you can
manage
also share the
electricity
link
usage.
in the chat box, participants can see later also. Yeah, अभी दिख रहा है
It's
पहले
like we go have shared the same in the chat box, so you may be able to see the same later on.
By measuring a home's electricity consumption more frequently through a smart meter, utilities can provide their customer with much better information to manage their electricity bills. Inside the smart home, a home area network, or HAN, connects smart appliances, thermostats, and other electric devices to an energy management system. Smart appliances and devices will adjust their run schedule to reduce electricity demand on the grid at critical times and lower consumers' energy bills. These smart devices can be controlled and scheduled over the web or even a TV. Renewable resources, such as wind and solar, are a sustainable and growing source for electric power. However, renewable power sources are variable by nature and add complexity to normal grid operations. The smart grid provides the data and automation needed to enable solar panels and wind farms to put energy onto the grid and optimize its use. To keep up with constantly changing energy demands, utilities must turn power plants on and off depending on the amount of power needed at certain times of the day. The cost to deliver power depends on the time of day it is used. Electricity is more additional, often run to meet the high demand. The smart grid will enable utilities to manage and moderate electricity usage with cooperate with their customers, especially during peak demand times. As a result, utilities will be able to reduce their operating costs. By deferring electricity usage away from peak hours and having appliances and devices run at other times, electricity production is more evenly distributed throughout the day. The power being used right now was generated less than a second ago many miles away. At each instance, the amount of electricity generated must equal the consumption across the entire grid. Smart grid technologies provide detailed information that enables grid operators to see and manage electricity consumption in real time. This greater insight and control reduces outages and lowers the need for peak power. In control rooms across the grid, engineers will be able to more precisely and predictably manage electricity production, reducing the need to fire up costly secondary power plants. The distribution system routes power from the utility to residential and commercial customers through power lines, switches, and transformers. Utilities typically rely on complex power distribution schemes and manual switching to keep power flowing to their customers. Any break in this system caused by storms, bad weather, or sudden changes in electricity demand can lead to outages. The smart grid's distribution intelligence counters these energy fluctuations and outages by automatically identifying problems, then rerouting and restoring power delivery. These can further use distribution intelligence to predict and manage electricity usage with the cooperation of their customers, leading to lower production costs. The charging of a plug-in electric vehicle can be managed over a home area network, or HAN. HAN is demand for electricity across the house and prioritize between the electric vehicle and other lines and reduce costs. With smart grid technologies and consumer participation, utilities can more easily handle the increased demand for power to run the electric vehicles and ensure charging needs are met. By adding more plug-in electric vehicles to the grid, We have the potential to reduce fuel costs, lower our dependency on foreign oil, and help reduce greenhouse gas emissions.
All right. All right, then moving ahead to the rural electrification part of India. So no wonder different states are working there with their own capacity to provide electricity to the last part of the of their on state. But yes, rural electrification has their own challenges established with it. For an example, if I give an example of Punjab, you may find that okay, in Punjab every village has the electricity, but then you may also find the energy security basically means to provide the power supply at an appropriate cost or at a lower cost for 24 hours. Okay, the major challenge which majority of people face, and specifically this happens in Kashmir as well. I was preparing the action plan for Kashmir also long back, and we face the same kind of issue in Kashmir. The electricity they used to get in the summertime, they have a higher hydropower potential, so they have a huge hydropower plants as well. Um, because of the hydropowers, they have huge electricity, and in the summer, uh, they have huge electricity. But in the winters, when the water gets solidified, at that time the hydropower generation reduces to a significant number, and that time it becomes very difficult for the utilities to in fact provide 8 to 10 hours of electricity to different villages as well. For many of the villages, in fact, or in fact many of the cities also, have electricity less than 14 hours a day. So that's why it becomes a challenge, and specifically in the rural area, to provide the electricity to the last point of the state. It becomes a challenge for the state. But yes, it must be admitted that India has done well in the same part. And another thing is the installed capacity of the country has been doubled over the 7 years, and it is projected to grow further. Um, the bigger part is nowadays every household has more electrical systems than it used to be in the last few years, and every households nowadays have AC. There was a time when the AC was considered to be luxury, but now every household have an AC. Electrical motors are there, and fans, lights, and computers, LEDs. TVs and everything. Every household used to have microwave oven and these stuffs. Every household nowadays have these kind of facilities at their home. Then not only the installed capacity has been increased, but also the grid distribution network has also been expanded now. And household electrification, India has been able to reach 99% of the household electrification. And recently, you might have heard about that India have provided electricity to each and every village. The challenge India now facing is to provide 24 hours of electricity to the people. That is the only challenge India is currently facing. Then the per capita electricity consumption in India, the per capita electricity consumption is low, which is way too lower than the developed countries. But the bigger problem is the population of population of the country, and because of that population, our total energy consumption is far more higher than the energy consumption of those countries. So that's why population control itself is a challenge. But yes, India is looking forward to reduce their per capita electricity consumption, though in the eyes of policymakers, the increase in the per capita energy consumption, it means that the country is growing. So more the per capita energy consumption, it means the more towards development we are moving. So that's another aspect. But yes, per capita energy consumption could be reduced by using the efficient systems. That's what the target of the government is. And on the aspect of utility, the supply hours, evening supply hours, metered consumption connection, on-time billing, and complaint redress, and stable voltage. This is what satisfy a customer in the terms of electricity. The utilities have to meet these targets, which is sometimes a challenge with the rural electrification. Then average per unit realization, these are the figures of 2017, in which if you see rural, the tariff per unit is way too low, 2.90, but the cost per unit, which is on the higher side, 8.30. And then because of that surplus gap, rural electricity in the rural area is a bit challenge. Um, Then the primary source of electricity, which the household use in the rural area, basically mini grid 1.5%, major grid is 71%, and then solar home system, solar lanterns, and diesel genset, rechargeable batteries, kerosene lamps, torch candles, emergency lights, somewhere in range of 27%. And then the bigger challenge with the rural areas, the rural area faced with the utility is, one is the power cuts. It becomes difficult for the utilities to provide more than 8 hours of electricity to the rural areas, and then poor metering and billing. High number of unmetered connections are there in the rural areas, and the billing is highly irregular. Many a time it does happen that for 3 months or 5 months, nobody from the electricity department comes to check the billing, and then they just take the same number for the 5 months. It does happen. It's very irregular, and that's where the dissatisfaction comes up. This specifically happens in the case of farmers when. As the electricity for farmers is free, so the PSPC will provide free electricity to the farmers, but PSPC will take the same amount from the state government. So when they take the amount from the state government, they calculate those numbers as well, those numbers as well, which are unmetered. Basically, those pumps as well, they take it from the unmetered part. So many a time they don't even visit the site. They just take the same thing just anyway. They just take the numbers. I mean, the numbers could be the discrepancies are there in those numbers. So that's what the unmetered connections are there, and that's why the poor metering is another challenge. There are few myths as well which has been associated with the rural areas, which is rural electricity demand is low, which is not true. And nowadays villages have ACs, villages have motors and every kind of stuffs. So which itself is not that true. And there was a myth that rural customers cannot afford electricity, they do not pay high rate of theft is there, which are basically myths. That's not fundamentally true as far as rural electrification is being concerned. A case study has been done in which they analyzed 19,000 numbers of customers across 150 plus smart power mini grids in India, and then they determined that okay, these many are the people, 98%, 99% are the people who are reliable to pay. If the service is reliable, they are able to pay. They are paying the same part. So if the number is more than 90%, we could consider that okay, in rural electrification, India should not. Though the last review was considering them as myths, because in rural areas specifically, utilities initially used to have these kind of myths that okay, they have lesser demand and that kind of stuff, but that's not fundamentally true. The rural, apart from the government systems being installed in the rural areas, the buildings itself in the rural areas are very much having each and every kind of systems being installed. The government buildings, let's say if there is a school, government school, and they may not be having the ACs, but yes, the households in the rural areas, they have ACs, TVs, and every kind of that stuff. All right. Similarly, the collection efficiency in the grid areas with improved services, more than 85%. So which is again a fundamentally fine figure. Similarly, in the perception of affordability, if they are able to afford the same or not, so which is also in the fine figures. Similarly, low income segment also, if the low income segment, if they provided the electricity, their electric consumption increases with increased hours of supply. So initially, if they were providing low income, they were providing 31, let's say they were providing hours of electricity for 13 hours, and then when they switched to 20 hours, the energy consumption also increased. So it does not mean that if the income is low, people would use less electricity. Electricity is the basic need, and people fundamentally use the same. So there is also one more thing that is being true, is the rural micro enterprises, the small industries or the small scale industries being installed in the rural areas. They are high consuming and paying customers with a stable demand. So these are small industries, but no wonder they are paying. They are able to meet the demand, and they are able to pay to the industries, to the utilities, and no wonder they are running their own system with some challenges like to getting the electricity for lesser hours. I have seen a lot of industries in Kashmir in the winter part. They have to pay the salaries, yet they get the electricity only for 8 hours or 9 hours. So that's again kind of challenges which these micro enterprises face in the rural areas of not getting continuous electricity, and they have to rely on non-grid sources like diesel generators, solar systems, batteries, etc., which they have to rely on. All right, so India came up with a new scheme. This is they came up with this scheme in 2013, which is Deen Dayal Upadhyay Gram Jyoti Yojana, which is for the rural areas, and which has uh, majorly it has three components. One is to segregate agriculture and non-agriculture feeders. It means the feeders which is directly being connected to the agriculture pumps, and another feeder which is being connected to the non-agriculture areas. So that's to segregate both of these, so that they could directly get to know that this much is the energy which is being consumed to the agriculture part. Then strengthening and augmentation of sub-transmission and distribution infrastructure in rural areas, including metering of distribution transformer, feeder, and the consumer end. So the time we were talking about the indirect method, in which we were talking about metering at the transformer, feeders, and consumers end. So that's what their target is, to strengthen the same. Then finally is the rural electrification, is another in their plans of 12th and 13th plans. Initially, there was a Rajiv Gandhi Yojana of Gram Vidyut Yojana, and then they subsumed it into Deen Dayal Upadhyay Gram Jyoti Yojana, and then in which the target is to electrify each and every village of the country. And then it's true that they are able to meet the same. They have electrified each and every village of the country. But yes, the few challenges which every village is facing is the 24-hour supply of the electricity, which many of the villages are facing. So for which the utilities are working on the same. Then another target is to prepare a rural electrification data hub, which will include all the nodal information, data, and related to the rural power distribution system. And then they could use the data accordingly to electrify the country or electrify the state. Now, this is Office Memorandum, which was issued on 3rd December 2014 by Ministry of Power in respect of Deen Dayal Upadhyay Gram Jyoti Yojana, which includes the kind of fund Ministry of Power have provided in order to electrify the villages, and they have provided electricity to each and every kind of village. And in fact, if you see point number 2, it says the estimated cost of electrifying habitation above 100 population. So if it is a small village or a bigger village or whatsoever, yet electricity is the basic need, and that's what the targets are, to provide electricity to each and everyone. So that's what the estimate is. And if you require more details on the for the same, or for the rural electrification, you may visit to Deen Dayal Upadhyay Gram Jyoti Yojana website as well, www.ddugj.gov.in, and then you may find more information relevant to the same. So with this, I'll close my session. Thank you so much